In this video, we're going to talk about superposition and how to program our computer to do superposition. So let's draw out our energy states. Let's draw out our two-level quantum system. So electron volts on the vertical axis. We have our ground state, n equals 1. We have our first excited state of n equals 2. We have an electron here in the ground state, and we're assuming that the spin of that electron is spinning down, i.e. north is facing down, south is facing up. What we want to do now is apply an appropriate amount of electromagnetic energy to the system. So it doesn't spin to the up position, but it spins to somewhere in between. And the magnetic moment. So not only the electron voltage is in between, but the magnetic moment is somewhere in between a spin up and a spin down condition. To do that programmatically, we use the Hadamard gate. So let me draw that gate out diagrammatically. So it just looks like a H. And when we execute this gate, essentially we fire the specific energy at the system and we put it into a state of superposition. The matrix representation of a Hadamard gate is 1 over root 2, 1 over root 2, 1 over root 2, and minus 1 over root 2. And the minus being there so we don't lose any states, because again it's a reversible computing system, so we always have to be able to get back to where we came from. So if we draw our unitary circle now, I'll draw it here, like so. Our basis state here, and we call that our 0 state, and that's where our vector is pointing currently. Up here would be our 1 state, but we're not going there right now. And the vector for this is 1, 0. So we could do our matrix math here, multiply this by 1, 0, and we end up with the matrix 1 over root 2 and 1 over root 2, which corresponds to the Cartesian coordinates here, and we have our vector in superposition. Now we can only maintain superposition, a state in between, as long as we don't look at it or observe it, or in fact in our quantum computer we call it making the measurement. As soon as we make the measurement, it's going to snap to the spin up state or to the spin down state. Now this is a perfect quantum system, so it's exactly halfway between the two. It's a state of superposition exactly halfway in between the two. So when it snaps and when we make the measurement, there's a equal chance, a 50% chance that it'll go to a 1 and a 50% chance that it'll go to a 0. So to do that, we would create another block here in our quantum computer program, and we would call that the measurement block, usually defined by some kind of little analog dial that defines the measurement. So this here is a quantum state. Here we make the measurement, and then it will snap to either logical 1 or a logical 0. And if we did 100 measurements and plotted a histogram, we would find that 50% of the time it would be a 1, and 50% of the time it would snap to a logical 0. Noise affects the system, and you can never be exactly halfway in between. So in reality, you might say, 51% of the time it's a 0, and 49% of the time it will be a 1 if we make 100 measurements or 1,000 measurements. And noise is something that we're going to talk about in one of our future videos.